Building a cellular IoT device that works in one country is one challenge. Building one that works globally is a different challenge entirely. Let's look at the carrier landscape, roaming complexities, and regulatory considerations that affect worldwide cellular IoT deployments. Unlike Wi-Fi, which operates on globally harmonized, unlicensed spectrum, cellular IoT depends upon licensed spectrum allocated differently in every country. Each carrier in each country makes independent decisions about which technologies to deploy, which frequency bands to use, and which IoT services to offer. Standard 4G and now 5G are available pretty much worldwide in any geography. For IoT applications where higher amounts of throughput or low latency are required, these sets of higher category radio technologies are an obvious choice. Even for applications that do not require high throughput, choosing standard 4G or 5G, ideally choosing a modem that supports both, will maximize coverage options globally across the most number of carriers worldwide. Your modem and antennas should support the maximum number of frequency bands possible, and you should design your power supply around the needs of standard 4G and 5G whenever possible. In applications where it is not practical to support the power needs of standard 4G and 5G, Low Power Wide Area Network, or LPWAN, radio technologies can be considered as an alternative in advanced use cases. In North America, LTE-M is the dominant LPWAN technology. AT&T, T-Mobile, and Verizon all support LTE-M with nationwide coverage. NB-IoT is available on some US carriers but is less consistently deployed. In Europe, both LTE-M and NB-IoT are widely available, but the mix varies by country and carrier. Deutsche Telekom and Vodafone have been strong NB-IoT proponents, while others have rolled out LTE-M alongside it. In China, NB-IoT is dominant. China Mobile, China Telecom, and China Unicom have deployed massive NB-IoT networks supporting hundreds of millions of devices, primarily smart meters and urban sensors. In the rest of Asia-Pacific, the picture is mixed. Japan and South Korea have strong LTE-M and emerging 5G RedCap support. Southeast Asian markets are still building out LPWAN coverage. Latin America is seeing growing LTE-M adoption, while Africa and the Middle East are still in early stages for both technologies. Again, defaulting to standard 4G and 5G with wide multiband modems and antennas, or at least 5G RedCap, will likely maximize coverage and carrier support from now and into the future. For devices that ship from a factory in one country and deploy in another, or for devices that physically cross borders, like vehicle trackers and shipping containers, roaming is essential. Cellular IoT roaming works similarly to phone roaming. Your home carrier has agreements with visited carriers that allow your device to connect to the visited network. However, IoT roaming has complications that occasional phone roaming does not. 1. Permanent roaming restrictions. Some countries and carriers prohibit devices from permanently roaming on their networks. A SIM from carrier A may connect to carrier B's network as a visitor, but if the device stays on carrier B's network indefinitely, the carrier may eventually disconnect it. These restrictions are rare, but can create individual problematic markets in some cases. 2. Technology availability. For example, your home carrier may support LTE-M, but the visited carrier in the destination country may only support NB-IoT or neither LPWAN technology. For this reason, supporting a widely supported radio access technology like standard 4G and 5G can be an important device design consideration. 3. Data routing. In traditional roaming, data is routed back to the home carrier's core network before reaching the internet. This adds latency and can create regulatory issues if the data crosses borders. Fortunately, sophisticated cellular IoT providers optimize around this issue through regional points of presence and breakouts and geography-based routing, which can offer the same or similar performance as not roaming. The 5G standards also contemplate a future where roaming can use a local breakout to directly connect to the internet via the visiting network, although this will require the market to make this a commercial reality. Different carriers use different bands, so this produces frequency band fragmentation. A device designed for band 13, used by Verizon in the US, will not work on band 20, common in Europe, unless the module supports both bands. Modern multiband modules typically support 10 to 15 LTE bands to cover most global carriers, but you must verify band support for every target market. Different countries have different regulatory requirements for radio type approval. A device certified for sale in the United States, FCC, will need separate certification for Europe, CE Red, Japan, TELEC, Brazil, ANATEL, and so on. Each certification process adds time and cost. The industry is increasingly adopting eSIM, EUICC technology to address global connectivity challenges. With eSIM, a single physical SIM card can hold multiple carrier profiles. When a device arrives in a new country, a new local carrier profile can be downloaded over the air, avoiding permanent roaming and ensuring the device connects to a local carrier with full service support. The SGP.32 standard was purpose-built for headless IoT devices, enabling remote SIM provisioning without human interaction. Sophisticated cellular IoT providers offer multiple eSIM profiles, as well as profile orchestration to automate their delivery and selection, replacing a much older and less standardized technology known as multi-IMSI. In short, global cellular IoT deployment requires navigating carrier fragmentation, roaming restrictions, frequency band differences, and per-country regulatory certifications. Multi-band modules, eSIM technology, and carrier aggregation platforms help manage this complexity, but you need to plan for it from the start of your hardware design. The best device architecture is one that minimizes regional SK use and maximizes flexibility through software configurable connectivity.